Imagine 27 small, charged water droplets. If they merge into one massive drop, you might assume the voltage multiplies by 27, but the actual physics requires a different answer. This demonstrates why we must separate geometric scaling from linear scaling to determine physical properties. We define n identical small drops, each with charge q and radius r. The electric potential for one small drop is V equals 1 over 4 pi epsilon naught times Q over R. We'll use this baseline formula to derive the massive drop's potential. Now, those n small drops merge to form a new, larger drop with an unknown radius, capital R. We cannot simply add the radii of the smaller drops together. To find the new radius, we calculate the conservation of volume. The combined volume of the n small spheres equals the total volume of the new large sphere. We can simplify this equation by canceling out the constant 4/3 pi terms on both sides. To find the new radius, capital R, we take the cube root of both sides. This proves that the radius scales geometrically by n to the 1/3 power. Shifting focus from physical size, let's establish our second critical property, electrical charge. Under the law of conservation of charge, total charge is strictly additive. The new large drop's charge, capital Q, is simply n times the individual charge, lowercase q. Here is the core contrast. While geometric radius requires calculating a cube root, charge scales linearly as a simple multiplier. Now we establish the target equation for the new, larger drop's potential, calling it V prime. It uses the exact same framework as our small drops, but with our new capital Q and capital R. Pause the video here. Take the two boxed equations for Q and R and attempt to plug them into this V prime equation yourself. Successfully solving the problem from this point requires merging both the volume conservation rule and the charge conservation rule into a single electrical framework. Here is the substitution step. We replace the capital Q and capital R variables with their respective n-based formulas. The primary algebraic hurdle in this derivation is simplifying this specific fraction, n divided by n to the 1/3 power. Dividing identical bases means subtracting their exponents. 1 minus 1/3 leaves us with an exponent of 2/3. Reconstructing the full equation, that isolated n variable can now be pulled cleanly to the front as n to the 2/3. Direct your attention to the fraction grouped alongside our new n to the 2/3 term. This specific cluster of variables is exactly equal to our baseline potential, V, which we established at the start. We finalize the proof by replacing that entire block of variables with a simple V. Returning to our opening question, when identical drops combine, the voltage scales by the 2/3 power, not a straight multiplier. These are the three distinct scaling laws to memorize. Radius scales by the cube root, charge scales linearly, and potential scales by n to the 2/3 power. Applying these conservation laws allows you to navigate complex scaling problems that defy basic intuition.